So what we are going to now look at is analysis of iterative algorithms. So means iterative is not recursive, that's why I mean non-recursive here. Alright, so before we look at the algorithms and some cases of how to analyze them, so let us look at these formulas. You should have seen this in your math class, some of them at least. But we'll see everything put together here, and we'll apply these formulas several times in the scopes and a lot in this module. Okay. All right. So if you have something like this, sigma, how to put it? Okay. So index I equals L to U. So it's like a lower limit, and this is or lower bound, and this is the upper bound or upper limit. Okay. Now this is like a summation is equivalent to a for loop in your program. Okay. So if I have a program something like this, for the loop index I equals 1 to n, and let us say print some hello or something. How many times we are printing this hello? We are going to print it I equals 1, I'm going to print one time, then I equals 2, I'm going to print one more time, equals 3 once, similarly so on up till I equals n. So you have to count how many times, how many integers or values are there between 1 and n, including 1 to n. So you may say the answer is simply n, right? But if you try to make things little interesting like this, so I equals say 4 to say 17, print hello. Now how many times you are printing the hello? Okay. Any answer?
We stopping at 17?
Yes, so we start printing from I equals 4. So this is the loop index runs from I equals 4. So when I equals 4, we are printing a hello. Then when I equals 5, you are printing again. So we do keep going like this until I equals 17. Okay. So if you want to count how many times you are printing this, you could manually count 4, 5, 6, 7. So when I equals 4, that's the first time you are printing. When I equals 2, that's the second time you are printing. Then third time. So on. What is the count when I equals 17? That's what we want to know. So the simple way to look at it is using this formula, which is going to be the same as you count. That's like upper limit minus lower limit plus 1. So the upper limit is 17 minus lower limit plus 1. So you are starting from I equals 4 going up to I equals 17 including 17. So that is why you are doing plus 1. So how many integers are between 4 and 17? You may say 17 minus 4, but that will exclude the one of the extremes. So in order to include the extreme value also, we are doing plus 1. So this is the formula. So 17 minus 4 plus 1 is 14. So we are going to print it 14 times. Okay. So that's what I have given here as a formula. So if we have a summation, so that's like equal to a for loop, I equals L to U, the lower limit to upper limit, and here I am just like the print statement. How many print executions you're doing for each iteration? One execution, right? So that is how we have to interpret this. So this is our basic operation. So how many times we are running our basic operation for each iteration? One time. So that's what goes inside the summation. So if you want to evaluate the time complexity of this for loop, this is how you would do it. Find the lower limit and upper limit and put inside the summation how many times you are doing the basic operation for each iteration. So for a particular iteration, we are running the basic operation once. So that's why we have 1 inside. And the formula is upper limit minus lower limit plus 1. Now, how would you evaluate something like this? Print hello, and then in another line, you are printing say world. How would you evaluate a for loop like this? How many times you are printing? Any answer?
Once you still use the same formula.
Use the same formula, but are you still printing 14 times?
Yeah.
Okay, but you have to understand you're printing separately. Print hello, and then in another line or something you're printing world. So you're doing what? 2 print executions for each iteration, right? So that means the formula should look like this. Let me try to use equation editor. So it's going to be like what? I equals 4 to 17. What should go inside the summation? 2. So I equals 4 to 17 2 times. Doing the basic operation 2 times for each iteration. Okay, is that clear?
Yes.
Okay, so now how you solve this summation? Take the 2 outside, it's a constant, right? So I can take the 2 outside and write this summation as I equals 4 to 17 1. So this 2 is a constant and it can be also written as 2 times 1. So I can take the 2 outside and get it in this format. Once you get it in this format, we can apply our formula. So that is 2 times 17 minus 4 plus 1, upper limit minus lower limit plus 1. So that is 28. Is that clear?
Yep.
Okay, so let us now look at this format, so that the other ones we look at is all they are also in this format. So the lower limit is 1 and the upper limit is n. So I equals sigma I equals 1 to n 1, and the only rule we have to only criteria we have to check while applying this formula is the what is inside the summation should be a constant. Okay, it could be 1, 2, anything. If it's anything other than 1, like we did in the earlier example, you can take that constant 2 outside, or whatever the constant it is, you can take it outside and still apply this formula. So what should be inside the summation is a constant. Then we can say upper limit minus lower limit plus 1. So here we have sigma I equals 1 to n 1. So we can apply that formula because 1 is a constant in the summation. So n is upper limit minus lower limit, which is 1 plus 1. So n minus 1 plus 1 is n. And n we know can be written as theta of n. Okay. So that means if you have summation of this format, sigma I equals 1 to n, and we have a 1 a constant inside the summation, it is theta of n. So if you have say 2, we got 2n, right? Because 2 times like 14, we got 28. So 2n is still theta of n. So that's why you could have any constant inside the summation. As long as it's a constant and the sigma equals 1 to n, we can write it as theta of n. That is something you should understand. Okay? Any question on this? Okay, so let us continue with the other formulas. Now instead of 1, let us say we have I inside the summation. So I equals 1 to ni. Okay, so this will correspond to what? So if you have sigma I equals 1 to n I, that is equivalent to telling how would the summation look like if you kind of open up the summation, substitute different values of I. So sigma I equals 1 to n I is same as writing, so I substitute the different values of I. So I equals 1, 1. That's what we have inside summation. So it's summation, so plus I equals 2, we have I. Then I equals 3, I. So on up to I equals n. So this is like 1 plus 2 plus 3 up to n. And you should have seen a formula for this in your math class. That's going to be n times n plus 1 over 2. That's the formula for this. Now we can simplify this because we want finally in a theta format. If you simplify this, that's going to be this n square plus n over 2. And you see how to get the theta notation. We can discard the lower order terms. So the lower order terms is this n over 2, and that is going to be simply n square over 2. So when we have n square over 2, again we can discard the coefficient, which is 1 over 2, and simply say this is n square. And n square, that is what goes inside the theta notation. We can say this is theta of n square. Okay, so if we have I inside a summation and it is I equals 1 to n, we can say that is theta of n square. Right? So let us continue now. If you have I square instead of I, so that is like this. So you have I square instead of I. So substitute the different values of I. For I equals 1, you are going to then have 1 square. For I equals 2, you are going to have 2 square. Similarly, we are going to have 3 square and so on up to n square. So if you have something like that, the formula is n times n plus 1 times 2n plus 1 over 6. So that's the formula for 1 square plus 2 square plus 3 square up to n square. And if you simplify this by just picking the highest, most dominating term, we are going to have n cube. Now I'll tell you an easy way to solve some formulas or expressions like this. So let me write it down here. If it is a board, we could easily write it up in class, but this is how it is. So n times n plus 1 times 2n plus 1 divided by 6, right? Okay, so we can split it up into 3 terms. One term is n over 6 because it's all multiplication. So then I can say the second term is going to be n plus 1. Well, I'll keep it like this. I'll take the 6. Okay, let us do it more simply like this. We'll take the 1 over 6 as a constant overall outside, then becomes more easier to look at. So this is n times n plus 1 times 2n plus 1. So we can write this as 1 over 6 times. Now n, as we know from our previous knowledge, n can be written as theta of n, right? Then n plus 1 can be also written as theta of n, so that's another theta of n. Then 2n plus 1 is also by itself can be written as theta of n. So 2n plus 1 is theta of n, n plus 1 is theta of n, n is also theta of n. So we have theta of n times theta of n times theta of n. So that is nothing but theta of n cube. Okay, so now we can discard this coefficient and simply say that the whole thing is theta of n cube. Okay, so any question on this? So just like you can do it that way, or even discard the lower order terms here. So if you discard the lower order terms in each of this case, so this is n plus 1, so discard this 1, so it's simply n. 2n plus 1, discard the coefficient lower order terms 1, and then the coefficient. So it's simply n times n times n is also n cube. So any way you look at it, it should be the same way you get it. Okay, so any question on these three formulas so far before we proceed?
No.
Okay, so we can kind of generalize things now. If I have 1 inside summation, which is 1 can be also written as I raised to 0. Anything raised to 0 is 1. You probably know from math, right? So 1 can be written as I raised to 0. So if I have I raised to 0 and I is from 1 to n, it is theta of n. Then this is I raised to 1 is theta of n squared. This is I raised to 2 is theta of n cube. So you see a trend here. The exponent or the degree of the polynomial inside the theta notation is 1 more than what is the exponent of I. If it is 2, it is I raised to 1. If it is 3, n raised to 3, this is I raised to 2. So if it's n raised to 1, 1 less than that exponent is 0. That is I raised to 0. So in general, we can say sigma I raised to k, I equals 1 to n, is theta of n raised to k plus 1. So one more degree, one more like 1 plus 1, k plus 1. Okay, so this is very useful, and we'll see some examples later. This is a very useful generalization to solve summations of this format. Okay, now we'll see one last formula and then we'll go to some examples. So if you have, instead of I being not an exponent, so here I is not an exponent in any of these cases. What was an exponent is just a constant like 1, 2 or 0. Now instead you have a constant in the base like a and I in the exponent. So sigma I equals 0 to n, and note that it starts from 0 instead of 1. So a raised to I, and what's the formula for this? So let us substitute the different values of I. So if I is 0, it becomes a raised to 0. Summation, so plus a raised to I equals 1. So a raised to 1 plus a square up to a raised to I equals n, a to the power n. So there's a formula for this. Summation starting from a raised to 0 up to a raised to n is a raised to n plus 1. So this is one term minus 1. So this minus 1 is not part of the exponent. This is a separate term. So a raised to n plus 1 minus 1 divided by a minus 1. And since a minus 1 is the denominator, you can apply this formula only if a is not equal to 1. Okay. Of course, if a equals 1, 1 raised to anything is going to be 1. Then you can revert to this formula. Okay. Alright, so let us take an example here. If a is 2, so sigma I equals 0 to 10, 2 raised to I. So make sure the I starts from 0 before you apply this formula. So yes, in this case, yes, it starts from 0 as in the formula here. So it is going to be 2 raised to n is 10. So 10 plus 1 minus 1 divided by 2 minus 1. So 2 raised to 10 plus 1, 11. So 2 raised to 11 is 20, 48. Minus 1. divided by 2 minus 1 is 1, so that's why I did not show up that here. So this is 2047. Okay, any question on the summation formulas? Okay, let me stop this.